I'm Kurt Thorn from UCSF, and today I'm going to tell you about a very famous microscopy experiment, the Abbe Diffraction experiment. And mostly we're going to be in the lab today doing a demonstration on a custom-built optical system. But before we go into the lab, I want to just give you some introduction to this experiment and its historical background and what it shows about the microscope. So this man here is Ernst Abbe, who is one of the founders of modern microscopy in a sense. He was active in the late 1800s working with Carl Zeiss and others in really formalizing the performance of the optical microscope and learning how to build diffraction-limited objective lenses, and in fact was one of the people who identified what was actually limiting resolution in the light microscope. And his diffraction experiment, the Abbe diffraction experiment here, is how he formalized that definition of resolution. And that resolution definition is in fact very famous. You've probably encountered it in other lectures already, that the resolution limit is lambda over the numerical aperture, or the refractive index, times the sine of the largest angle you can collect. And this is so famous that it's actually written in stone on his monument here at Jena. So what is the Abbe diffraction experiment? So the Abbe diffraction experiment is a way to think about what the resolution limit of the light microscope is. And Abbe's idea was to consider a striped sample. So the idea is we're going to take a sample with periodic stripes in it and ask, how finely spaced can those stripes be? How close together can those stripes be while we can still resolve them? So if we start with a very coarse grating, very coarse striped sample that has stripes spaced very far apart, they'll be easy to resolve. We can gradually make them more and more closely spaced until at some point we won't be able to distinguish one stripe from the next, and we'll just see a featureless blur. And this turns out to be really easy to analyze theoretically because of what a striped sample is, which is that basically a striped sample is a diffraction grating. So here is the optical path of our light microscope. Here's our sample in green. That's the striped sample here, this diffraction grating. And then we've got a light source here, a condenser lens here, so that collimates the light and illuminates the sample. And then up here we have an objective lens, which captures the light that's scattered off the sample and then collects it. And up off the slide not shown would be a tube lens and a camera or an eyepiece, so the lenses that would then relay this to a final image. But for today's discussion, all we really need to consider is the objective lens. So this is our objective lens here, schematically drawn as a lens, and it has some back focal plane here where light that leaves the sample at a constant angle will be collected and focused to a point. So if we consider illuminating with a point on axis here, what's going to happen? So we come in with this collimated beam of light from below. It interacts with our sample here, and our striped sample, remember, is basically a diffraction grating. So this is going to diffract that light beam. And in fact, it's going to diffract it through some angle, beta here, and the diffracted angle beta will be described by Bragg's law. And so the first order diffracted beams here will just be d sine beta equals the wavelength of light. So knowing the wavelength of light we're illuminating at and the stripe spacing here, we can calculate that diffraction angle beta. And provided beta is less than the largest angle than the objective can collect, provided it's smaller than the numerical aperture, what's going to happen is this light will be collected by the objective, make it through the back focal plane here, and then this can now interfere and be focused to an image by our tube lens, and we'll get an image of this grating. So you can see that the angle here is going to depend on the stripe spacing d, and so if I make the stripe spacing smaller, as I move those stripes closer together, this diffraction angle is going to get larger and these beams are going to move outwards. So that's shown here, and now we're looking at a case where the diffracted angle is larger than the largest angle than the objective can collect. So this is now an diffraction angle that's larger than the numerical aperture of the objective. And so what happens? These diffracted beams come out and they're not collected by the objective lens. They impact the back focal plane here and they're not transmitted. And so all we get through this is this undiffracted light that's going straight up through the objective without really being affected by the sample. And so this light here doesn't have any information about what the stripe spacing was. Here, the information about the stripe spacing is all contained in these diffracted beams, which we're not collecting. And so In this case, we're going to get an image of the sample that just is a uniform gray image. There's no information about the stripes here. We don't see any of those stripes. We just see transmission of some light through the sample. And so this is now a sample that has too fine structure to resolve by our objective lens. So if beta is greater than alpha, where alpha is the largest angle the objective can collect, then we don't get interference between these beams and we don't get an image. And so this is above our resolution limit. And so if we just set beta equal to alpha, so if we ask what's the very smallest stripe spacing we can see, what's the largest diffraction angle that we can actually collect with that objective, and we do the math, then you would find that the resolution here is just equal to the wavelength of light divided by the sine of the largest angle that the objective can collect, and then there's this factor here of the refractive index. And so this gives us the well-known resolution limit of lambda over NA. Often you'll see lambda over 2NA, and that's because you can get a factor of 2 improvement here if you don't illuminate with light that's on axis here, but you allow the full range of angles to illuminate the sample as well. And so this is the argument that Abbe used to work out what the resolution limit of the objective lens is and show that it's governed by the largest angle it can collect. And it also shows you something else, which is that the diffraction in the sample tells you something about the size of objects in it, and then interference between those diffracted beams are what gives rise to your image of the sample. And Abbe summed this up in a very famous quote where he said, the microscope image is the interference effect of a diffraction phenomenon. So you have diffraction from your sample, and then interference between those diffracted beams that gives rise to your image. And that's what we're going to now go into the lab and show you. We're going to look at various samples, see their diffraction patterns, and then see how interference between those diffracted beams gives rise to the image of the sample. What I want to do here today is try and give you a real-life demonstration of how this works with real optics and a real microscope. So the optical system in front of me is actually a microscope, although it may not look very much like any microscope you've used before. This is a system built out of simple optical components so that we can get access to all the planes of the microscope for demonstrating these principles here. But in all respects, it is really analogous to the kinds of upright and inverted microscopes you've used. What we've got here is a transmitted light microscope. We've got a lamp source on the left here, and then a camera on the right. And the optics between here are all exactly analogous to the optics you would see in a conventional research microscope. And I'll walk through them now from left to right, illustrating what each optic is and what it's doing. So on the left here, we've got an LED light source. It's mounted in this assembly here with a collector lens. So there's a lens here that's collecting this light and focusing it out to infinity in a parallel bundle. The LED is controlled by this knob here, so we can turn it up and down, make it brighter and dimmer. And then the optics in here are the condenser optics for this microscope. Starting with the object closest to the LED, this is our field iris. So opening and closing this iris controls the region illuminated on our sample. Then we've got our field lens. This is a color filter, so this is just a green filter I can put in to get green monochromatic light to my sample, and we'll mostly be using that to avoid issues of different colors having different behavior in this microscope. This here is my aperture diaphragm, my condenser diaphragm. So opening and closing this iris controls the range of angles that illuminate my sample, and we'll mostly be leaving this closed so that we're illuminating with just a pencil of light going right down the center of our sample here with parallel beams of light. And this then is our condenser lens, and so this lens is then focusing the light onto the sample. And this whole system is set up for curler illumination so that the LED here is in the back focal plane of the condenser, and then this field diaphragm is conjugate to the sample plane. This is our sample holder here, and then this is our objective, and this is just another simple lens. It's another plano-convex lens mounted in a lens holder so we can screw it in and out to focus it. We have another sample holder here, and this one is located at the back focal plane of this objective. And I'll have a lot more to say about this later in the lecture. Then one unique thing about this microscope, and the reason we built it this way, is we have a beam splitter here so that we have two different detection paths. The straight-through detection path here is a conventional microscope. This is our tube lens, and it images our sample onto the camera. So whatever is in focus in our sample plane here is in focus on our camera. The other path reflected off the beam splitter is a path that allows us to image the back focal plane. And so this lens here is acting as a simple magnifier lens to project the image from this back focal plane onto our camera here. And so on the laptop, I can switch between this camera and this camera to see either the sample plane or what's going on in the back focal plane of the microscope. So let me start here by focusing on a simple grating slide. So you can see here the sample that's in focus right now is just a simple pattern of vertical lines. So these are just metal lines deposited on a glass slide, and the metal lines don't transmit light, so they're dark, the glass transmits, and so it's clear. If we now switch cameras and look at the back focal plane, and we turn this down, and then I need to close this. What you can see now is that this gives rise to a set of diffraction patterns. So let's just adjust the brightness. Let me close that down as much as I can. So you can first off see that the size of these disks here changes as I open and close the aperture diaphragm. And so the central spot in this image is the image of this aperture diaphragm. This corresponds to light that's making it straight through the microscope without interacting with our sample. The two closely spaced beams on either side of it are light that's been diffracted from this grating. So remember that a striped sample here, so this alternating pattern of dark and light lines, is going to act like a diffraction grating, and it will diffract light, and these are the first two diffraction orders. If I make the light brighter here, you can see they're not the only diffraction orders, and in fact, there are a whole bunch of diffraction orders that extend out to much larger angles. And the white vertical stripe you may see here is actually an artifact of the camera, so you can safely ignore. OK, let me switch back to my image camera here. So again, here's my grating image. And now I have many different gratings printed on this slide, so I can just slide over here. And now, if you look at this grating, let me make it a little brighter. You can see that this is a very fine stripe spacing grating. So you can see here that the lines are much more closely spaced together than in the previous grating. So if we now flip to the back focal plane camera, you will see that these more closely spaced lines correspond to much larger diffraction angles. So first thing to learn from this experiment is that position here in the back focal plane tells you something about the size of your features in your sample. So things close to the center of the back focal plane correspond to low spatial frequencies, so large-scale structures in your image, things that don't change very fast as you move across the image. Whereas positions further out in this image correspond to high spatial frequencies, so regions of the image that change very rapidly as you move position. So because this grating has very closely spaced lines, it has higher spatial frequencies, and so these first diffraction orders are located further out in the back focal plane than the grating that had coarser lines. Like the previous one, this also has higher order spots. The other thing to realize here is that not only does the position here tell you something about the size of the structures, but it also tells you something about the direction of those structures. So both the gratings we've looked at so far are vertically oriented lines. And so a diffraction grating with lines oriented vertically is going to scatter light perpendicular to the line orientation. And so that's why we get a line of spots here that's in the horizontal direction. If instead we switch to a grating with a different orientation, we'll see a different pattern of spots. So let's switch back to the image plane again. And now I have to look for one. So here now we have a grating that's oriented in the horizontal direction. And so based on what I've told you so far, we would expect that the diffraction pattern from this should be oriented in the vertical direction. So let's switch to the back focal plane and find out. And yes, exactly as we expect, we now see a set of spots located in the vertical direction. So we're getting now information about these lines that are in the horizontal direction shows up in the vertical diffraction pattern in the back focal plane of the microscope. So let's switch back to the image plane again, and now ask, what do we see if we put in a two-dimensional grating? So I'm going to switch slides now, take this guy out, and put this in. And our two-dimensional grating here is just an ordinary stage micrometer. And so this is just a grid with 10 micron lines that you would buy to focus your microscope, or to calibrate your microscope, rather. And get that in focus. OK, so now we have a nice image of a 2D grid here. And based on everything I've told you so far, we would expect that this should give rise to diffraction in both directions, because it has both horizontal lines and vertical lines. So again, we'll switch to the back focal plane camera. And indeed, that's what we see. So we've got our zero-order light here. So this is the central spot is the undiffracted light making it through our system, which hasn't interacted with the grating. And then we see these horizontal and vertical spots diffracted by the grating. And again, this vertical stripe here is a camera artifact from this bright central blob. And some of these this guy over here is a back reflection. OK, so now hopefully you've seen that position in the back focal plane tells you about both the spatial scale of your structures, so the size of your structures and how closely spaced they are together, and also their orientation. Now what I want to show you is that, in fact, this image here in the back focal plane contains all the information about your sample. And everything you can see in your sample is encoded in the back focal plane. And furthermore, if we manipulate what makes it through the back focal plane by blocking some of this light, we will change what we see in the image plane at our image camera here, because we've removed that information from our image. And so to do that, we have a set of patterns here. And so these are just similar metal masks that we can position in the back focal plane to prevent this information from making it to the camera. So I'm going to start here by blocking all the vertical light. So I will slide this grating in and then position it height-wise. And so you can see now I've got this set of two black bars here so that they're cutting off all the light from above and below here. We're only letting through now the band of horizontal diffraction. And so now this diffraction pattern looks just like what we saw from our vertically oriented lines before. And in fact, if we now go looking back at our grating here, you see, in fact, we've lost all the information about the horizontally oriented lines, and we now just see a set of vertical stripes. So by blocking the diffraction information from the horizontal lines, we prevent our ability to image them, because that information doesn't make it to the camera. And just to prove I'm not cheating, if I slide this out, you can see the whole grid reappears. And if I slide it back in, then we just get our vertical lines again. There's nothing special about the vertical direction. I've got another pattern here, so let me switch back to the back focal plane so I can get it positioned properly. So if we now go and slide this pattern in, now we can block all the horizontal information. And so based on everything I've told you so far, you should expect to see just the horizontal lines. And in fact, that's exactly what you see. So hopefully I've convinced you now that the back focal plane of your microscope not only encodes all the information about spatial structures in your sample by their spatial frequency, but it's also a complete representation of that information. And blocking information there prevents you from retrieving that information in your final image. So that the back focal plane is the Fourier transform of your sample, not just mathematically, but physically. And that's how the information gets reconstructed by your microscope. So you have, essentially in a microscope, your objective lens generates a Fourier transform of your sample at its back focal plane, and your tube lens then resynthesizes that Fourier transform into a real image on your camera. So thank you.